Okay, well, good morning, everyone. I'm sorry that we can't all be together today due to the inclement weather, but nonetheless, I wanted to make sure that you had the content that you needed related to today's lecture so that we don't get behind a little bit further in the semester. And more importantly, that we make sure that you're adequately prepared for the exam that's coming up next week. So with that being said, today's lecture would have consisted of a few examples still taken from the Instant Centers portion of the class, which of course you can find on the blog under the lecture example videos link, as well as me discussing a number of the conceptual problems in the back of the book, and potentially doing one of the longer rigid body kinematics examples from section 2C of the book, which again you can find under the lecture example video segment of the blog. So the one thing that's not on the blog, as you know, and this is somewhat intentional on my part, is me actually solving some conceptual questions for you. This is because I'd like you to go through and use those as a self-test to see how good you are at having a high level of mastery about a particular subject. Today, though, I'm going to make an exception to that rule, given that we're not able to meet in person, so I'm going to go through here with you about 5 of the conceptual problems in the back of Chapter 2. I encourage you to follow along on these problems and then try the remaining problems in the section to see if you have the level of mastery that you're going to need to succeed on next week's exam. So with that being said, let's go ahead and dive in. So in this first conceptual question, we're told that the rigid body shown below has a counterclockwise angular velocity, and I'll go ahead and sketch that here for us, and a clockwise angular acceleration alpha. And we're told that the direction of the acceleration of A, point A, AA, is shown in the figure with AA being perpendicular to the line AB. So I can sketch in perpendicular here. We're asked to make a sketch showing the direction of the acceleration vector for point B. We're told that this sketch does not need to be accurate, but simply shows direction relative to the lines in the figure. Okay, so to help us out here, really all I'm going to do is I'm going to express the equation for the acceleration of point B. So in this case, and let me move it down here so we have a little bit more space to work, we know that the acceleration of point B is going to equal the acceleration of point A plus the angular acceleration of the object, which in this case is in the k direction. Actually, let me write it in full vector form first. So AB is going to equal to AA plus the angular acceleration of the rigid body across the position of B with respect to A. And then because this is a planar problem, I can subtract off of that omega BA quantity squared times R of B with respect to A. Now, what's probably going to be helpful in this problem is to set up a coordinate set. So I'm going to choose to go ahead and put my I unit vector along the line AB and my J vector to be perpendicular to that, if you would, along with this line which is passing through B and perpendicular to the line segment AB. Why do I want to do that? Well, because I can do a little bit of math now and make some good things happen. Namely, what I know here is that AA is a given vector for us. I know that AB with A, that is the angular acceleration of the rigid body, we're told is clockwise positive. So this can be written as minus alpha BA in the K, where in this case the scalar alpha BA is a positive number. I can then cross that of R of B with respect to A, and if I call this a distance D, that's going to simply be, in this case, minus D in the I. And then I can subtract off that the known value omega BA quantity squared times, in this case, minus D in the I. So if I go ahead and plug through the math here, what I'm going to have is something that's AA, the vector that we're given. K cross I gives me J, so I'm going to have plus alpha BA times D in the J. And I'm going to have plus omega BA quantity squared times D in the I. Now actually this is enough for us to sketch in the acceleration vector at point B. Why is that? Well, we know the acceleration A is purely in the J direction. That is, I could write this as some AA in the J. I'm adding that to two positive numbers which are multiplying each other in the J. And then I'm adding that to a positive number in the I. So the net result is that the acceleration vector at point B has to be somewhere in this first quadrant of the IJ coordinate space as shown here. And that would be the answer we're looking for in this conceptual problem. All right, let's try a different one. Let's try conceptual problem 2. Here we have a sphere of radius r that we're told rolls without slipping to the right on a rough horizontal surface. The center of the sphere O has a speed v0, and this speed is decreasing at a rate of a0, which means, of course, the acceleration vector is pointing in the opposite direction. Based on this information, we're asked to circle the drawing that most accurately represents the acceleration of the contact point C. Now this is a relatively straightforward process for us to go through. We know in this case that the no slip condition implies that the acceleration of point C in the x direction has to match that of its ground, and so we know in this case it's going to be 0. So right off the bat, I know that A, B, D, E, F, and H are all inappropriate answers. I'm now down to 3 of the initial answers that I had. Now, what about everything else? Is there something here that I can find out? Well, what I can do is I can say, well, I know the acceleration of O is going to equal the acceleration of C plus the angular acceleration of the disk cross r of O with respect to C minus omega squared r of O with respect to C. Let's see what I get here. I know that AO is going to be completely in the I direction. I know that AC is going to be completely in the J direction. Alpha, in this case, we can write as simply being an unknown value alpha in the K. I cross that with position O with respect to C, which is R in the J, and then I subtract off from that omega squared times R of O with respect to C, which is the distance R in the J. If I work on the right-hand side of this a bit, I'm going to end up with AC in the J. K cross J is going to give me an I component, and in particular minus I, so I'll have minus alpha R in the I, minus omega squared times R in the J. So if I now just pull up the J components of this, I'm going to find that the acceleration of point C, the scalar value for that, is going to, minus omega squared times R has to equal 0. This of course means that the acceleration of point C has to equal omega squared times R. Since the right hand side here is a positive quantity, I know that AC has to be pointing in the positive J direction by the initial assumption I made up above. In this regard, the correct answer for the system will be C, provided omega is not 0. And we know omega is not 0 here because the system does have a velocity at the center. Okay, so hopefully you got that one as well. Let's keep moving along here. Here in this problem, question 2C, we have a stepped drum which has inner and outer radii of R and 2R respectively, and we're told the drum moves to the left with its center O having a constant speed of v0 as shown in the diagram. We're told that points A and B lie on the inner and outer radii respectively of the drum, and at this instant, A is directly to the right of O, and B is directly below O. For this system, we're asked to make a sketch of the velocity vectors for A and B, and also to make a sketch of the acceleration vectors for A and B. Okay, now probably the easiest way to tackle the velocity part of this problem is to simply use the notion of instant centers. In this problem, we're given that there's a no-slip condition here at this point, which I'm going to call C, which of course means that if v0 is moving to the left, that the angular velocity of this drum, which I'll call omega, has to be counterclockwise positive. In addition to that then, I know that the velocity vectors at points A and B have to be perpendicular to the line connecting the respective point in the instant center. So if I draw my line down to B, I know the velocity vector has to be perpendicular to that, and if the object's rotating about point C with a counterclockwise angular velocity, I know the velocity vector for B has to look something like this. I can then draw a line up to point A, which will be here on this nice 45-degree angle, and I know that, again, the velocity vector has to be perpendicular to that line, and so in this case, again, noting that we're rotating in a counterclockwise sense, the velocity of point A has to be over here. Now, the second part of this problem asks us to actually determine what the acceleration vectors look like as well. There's a tactic I normally take to answering this question in class, which I hope that you like. Basically what I do here is suppose that I pick an arbitrary point on this body, and let's just call it P. I can say that the acceleration of point P is equal to the acceleration of point O plus, in this case, the angular acceleration of the body cross r of P with respect to O, minus omega squared times r of P with respect to O. Now do a thought experiment with me. If the system is moving with a constant speed at point O, and we know of course that O has to move in a horizontal line, then the acceleration term is going to be 0. Likewise, if it's moving with a constant speed, we know it has to have a constant angular velocity, which means that the angular acceleration is 0. The net result of this is that the acceleration of point P, wherever we choose that value to be, is going to equal minus omega squared times the position vector of P with respect to O. In other words, if I want to find the acceleration at any point on this object, wherever I choose to place P, it's simply going to be a vector that points towards the center of the object. So if I want to sketch an acceleration vector at point A, I know it's going to point right towards point O and have magnitude minus omega squared times little r. Likewise, if I want to find the acceleration vector for point B, I know it has to point towards O, and it's going to have a magnitude which is minus omega squared times 2r. Okay, that wraps up this problem. We have our acceleration and velocity vectors drawn. Please make sure you understand how to do this because I think it's very integral to what we're doing in the course. Let's do two more. Let's work a little bit more on instant centers, since I know that that's a subject that often students are a little uncomfortable with. Here we have a little mechanism, and in particular in this mechanism what we have is a collar B which is free to move vertically, and a rigid disk which is free to rotate about point O. And we're told that collar B and point A on the disk are connected via a rigid link. And at the instant shown, point A on the disk is on the same horizontal line as point O. At this instant, we're told the angular velocity of A, or asked to find that the angular velocity of A is at clockwise, counterclockwise 0, or we need values. Pardon me. So to find something out about the angular velocity of link AB, of course, we're going to want to use the method of instant centers, and we'll want to move towards points that we know the most, towards points that we know the least. In this case, I know omega OA, and if I note that the center rotation of this rotating disk is at O, I can use that knowledge, of course, to get that the velocity of point A in this case has to be pointing straight down. I also know that the velocity of point B is constrained to move along this path as indicated. So if I sketch in here lines which are perpendicular to the two known velocity vectors, one here and one here, I realize I get two parallel lines. Two parallel lines only intersect at infinity, which means that the angular velocity of this instant of link AB has to be identically 0. The reason for that, of course, being that omega AB has to equal, in this case, the speed at point A divided by the distance between point A and the instant center of link AB. Since that instant center is located at infinity, we know that we're going to end up with here something that's like omega AB is equal to a finite speed divided by infinity, which of course implies that it's equal to 0. Okay, so let's wrap this chapter up by doing one more conceptual problem. Here we have a little mechanism made up of links OA, AB, and DE. We're told that pins D and E on link DE are constrained to move along straight guides. Link OA is pinned to ground at O, and pinned to link AB at A. That link AB is also pinned to link DE at point B, and that pin D moves to the right with a speed of VD. For the position shown, we're asked to accurately determine the location of the instant center for link DE, the instant center for AB, and to determine if link AB is rotating counterclockwise, clockwise, or is instantaneously at rest. So the first thing I'm going to do is take the information we're given in this problem, which is that pin D is moving to the right with a speed VD, and I'm going to see how I can use that. Well, the way I'm going to use that is I'm going to say, well, listen, I know velocity of point D is to the right, but the velocity of point E has to lie somewhere along this vertical line. In other words, I know the velocity identically at one point on this rigid body, and I know the direction of velocity at the other. So what I can do is I can sketch in lines perpendicular to both of those velocity vectors, and I'll choose to do so here in blue. And I'll realize that the instant center of link DE is going to be somewhere where I've indicated here in the drawing. If I use this fact and also the fact that VD is moving to the right, I can additionally say here that omega DE has to be counterclockwise positive. If omega DE is counterclockwise positive, I can extend that logic then and say the velocity of point E is moving upward. Awesome, I now know a lot about that link. I need to work my way through the remainder of the mechanism, so to help me out with that, I'm going to note that the velocity of point B, because it lies on link DE, has to be perpendicular to the line from the instant center to point B. And so here, I'm going to get a velocity vector for B that looks something like this. Likewise, I know the velocity vector of point A has to lie somewhere along this horizontal line. So if I draw perpendiculars to both of those, which I'm going to do now, I'm going to get here one perpendicular to AO, or parallel to AO, and here continuation of this line. And so I'm going to find somewhere up here in the problem statement actually is the instant center of link AB. Now if I use the logic that VB is moving up and to the right, I know that omega AB has to be, in this case, counterclockwise positive. In addition, and to saying that omega AB is counterclockwise positive, I can say that the velocity of A has to be going to the right. And if I use the logic that the velocity of point A is moving to the right, and that its instant center of link AO is at O, then I know omega AO has to be clockwise positive. So we worked our way around this mechanism. We identified the two instant centers we were asked to find, namely IC of AB and DE, and we've determined that the rotation rate of omega AB is counterclockwise positive. Okay, I think that just about wraps up these conceptual problems for today. I encourage you to go over these and then go over the rest of them in the remainder of the chapter. And then when we come back on Friday, we'll go ahead and look forward to chapter 3. Take care, everybody.